Hello everyone. In this video, I'll walk you through the code I've written to create a brain tumor classification model using the powerful technique of transfer learning. So this approach allows us to leverage the pre-trained knowledge of a deep neural network to solve a new task. So our goal here is to classify brain MRI images into different categories like glioma tumor, meningioma tumor, node tumor, and pituitary tumor. So let's delve into the code and understand each step. So here we start by importing the necessary libraries including matplotlib, numpy, pandas, seaborn, opencv, and the mighty tensorflow. So we also bring in modules for data pre-processing and visualization. So here are some visuals that are used in the further code. So preparation and pre-processing. So before getting into this, let's talk about transfer learning. So we are using the VGG16 pre-trained model, a sophisticated convolutional neural network that's been trained on millions of images for object recognition. So it's like a neural network that already knows a lot about image features. So this model acts as our base model. So before we proceed, let's set the image size to 224 and define the labels for tumor categories. So we have also implemented image augmentation techniques like flipping and rotation to generate more diverse training data. So here is the augmentation part and here comes the list. So next we loop through each label and its corresponding folder in the training dataset. So using the OpenCV, we read and resize the images to match our defined image size. So we add them to the externally train list and their corresponding labels are added to the wide train list. So we also apply augmentation techniques to these images to further expand our dataset. So here comes our X-train and Y-train list. And this is the sample image from each label. And here comes our augmented data set. So the first column, it's the original image set and rest are the augmented data set of the original data set. And shuffling and splitting the data. So So we then split the data into training and testing sets using an 80 to 20 ratio. So let's visualize the distribution of these images using a bar chart. And here is the bar chart of training and testing images that is split into 80 to 20 ratio. So to adapt the labels for training, we convert them into numerical values and use TensorFlow's utility functions to one-hot encode them. So this one-hot encoding algorithm, it's crucial for feeding our data into the neural network. So yes, so finally we get back to our transfer learning adventure. So we take the VGA16 base model and freeze its layers to preserve its pre-trained knowledge. So, so before getting into the actual process, let's see the pseudocode for generalized transfer learning. Here is the pseudocode and here is the pseudocode for our model, that is VGA16 model. And here comes our base model architecture. So our base model architecture, VG16 architecture, is pre-trained on ImageNet as a base model for transfer learning. So this particular code loads the VG16 model without its top classification layers. So here and then it freezes the VG16 layers, and then it adds our custom classification layers on top of VG16. So these custom layers include multiple convolutional layers with batch normalization and ReLU activation, followed by global average pooling and fully connected layers with dropout and batch normalization. So the final output layer consists of a dense layer with softmax activation, which is designed for classifying input data into one of four categories. So here is the summary of a model, and so total parameters. So the total parameters are around 20 million, and the trainable parameters are around 8 million, and non-trainable are, as you can see, 14 million. And here's the layers of our VJ16 architecture model. And here comes a beauty, that is Adam algorithm. So Adam algorithm, so it maintains adaptive learning rates for each parameter, adjusting them individually based on the historical gradient information. So this adaptiveness helps the algorithm converge faster and handle different learning rates for different parameters. So for our brain tumor classification, Adam optimizes the model's parameters by iteratively adjusting them based on the gradients of the loss function with respect to the model's prediction. And here comes the callback. So we define callbacks for training, including TensorBoard for visual insights, model checkpoint to save the best model. So and reduce LR on plateau to adjust learning rates on the fly. And here, so yes, so here's the moment of truth. We train the model by leveraging the power of transfer learning. So a model learns from the pre-trained VG16 base model and adapts to our specific task. So we train it using the training data and validate its performance using a 20% validation split. So we have set 15 epochs and a batch size of 64. So the training history, here it is. So we have set total 15 epochs, and yes, so these the printed output shows the results of each epoch during training. So we observe the loss, accuracy, validation loss, and validation accuracy matrices. So notice how the validation accuracy steadily improves over time, indicating the model's learning progress. So we are saving the best model using model checkpoint, allowing us to preserve the highest validation accuracy achieved. So here comes the performance matrices. So yes, so to provide a visual representation of training progress, we generate two separate plots. So here it is. So the first plot illustrates the training and validation accuracy. So the blue line represents training accuracy while the orange line indicates validation accuracy. So this visualization helps us understand how well our model generalizes to new data. And similarly, we have the second plot that depicts the training and validation loss. So the red line represents training loss and the light blue line signifies validation loss. So these plots helps us identify any signs of overfitting or underfitting during the training process. And here comes the prediction. So let's move on to making predictions using our trained model. So we feed the testing data into model and obtain predictions by using np.argmax, that is used above in the code. We extract the class with the highest probability as our predicted class. So we also retrieve the true class labels using the same function. So we generate a classification report heat map to display matrices like precision, recall, and F1 score for each class. So the heat map provides an uh, an adaptive way to assess the model's performance across the different classes. So here, yeah. So additionally, we create a bar chart that shows the accuracy, macro average, and weighted average scores from the classification report. So this visualization offers a concise summary of the model's overall performance. And also additionally, yes. So additionally, we also visualize the confusion matrix heat map to understand the misclassifications made by our model. So this heat map illustrates how often each class is being predicted as another class. So this insight can be invaluable in diagnosing areas for improvement. So as we can see, there are four columns and rows as well. So if we see the first brown cell, there are 778 number of images that are correctly predicted, and the rest are the wrongly predicted. So there is 5% chance that this model can predict the image wrongly. And uh, if we come to our output, so this is how our output looks. Let me So in summary, this code loads and displays selected brain tumor images, predicts their classes using a pre-trained model, and presents them in a grid layout with relevant information. So, so the visualization allows for comparing predicted and original labels and image names for each displayed image. So this was it, and thank you for watching this video.